You know, when you're working with 3D software and you can just kind of pull and push these really complex shapes, almost like digital clay.
Yeah, absolutely. It feels intuitive on the surface.
Right. But have you ever stopped to wonder what's actually like going on underneath? What makes that possible?
Hmm.
It turns out there's this fundamental concept called a mesh that's, well, it's behind almost everything you see in computer graphics and design software.
Pretty much everything visual in 3D, yeah.
So today, let's do a deep dive into this fascinating hidden world.
Sounds great. We're essentially going to, dissect the DNA of these digital 3D forms today.
Okay.
And our listener, the learner, has given us some fantastic materials to work with. A whole workshop focused on computational mesh fundamentals and design.
Ah, excellent. What kind of materials?
We've got video transcripts, a briefing document. It really gives you a feel for that hands-on learning environment. They're using tools like Rhino and Grasshopper.
Oh, powerful stuff. Okay, so our mission today is pretty straightforward then. We're going to unpack the core ideas behind these meshes.
Right.
You know, how they're built, how we manipulate them digitally, and maybe most importantly, why understanding all this is so crucial if you're interested in computational design.
Definitely. It unlocks a lot.
We're aiming for those aha moments, but without getting totally bogged down in like super technical jargon.
Being accessible but informative.
Exactly. And to help us navigate all this, we have our expert here to connect the dots and maybe show us the bigger picture.
It's great to be back. And what's really interesting right from the start is how these complex 3D shapes are actually built from surprisingly simple parts.
Okay, simple parts. Let's start there. When we talk about a mesh, what are the absolute like core elements, the building blocks?
Okay, so at its heart, a mesh is really a collection of interconnected bits that define a 3D shape.
Bits.
Well, more specifically, the primary elements are vertices. You can think of them as just individual points in 3D space, X, Y, Z coordinates.
Got it. Points in space.
Then, these vertices, they get connected to form faces. Faces are the actual surfaces you see, the bits that make up the shape.
Okay, points connected to make surfaces.
And the crucial third piece is connectivity. This is the information that tells the computer exactly which vertices connect to create which face.
Ah, so it's like the instruction manual for connecting the dots.
Precisely. Imagine drawing lines between the points. Connectivity is the record of all those drawn lines forming the faces.
And I noticed from the workshop material, it sounds like one particular shape, one type of face, is kind of the star of the show.
Oh, absolutely. The triangle. The materials even say, I'll quote the Korean here, Dogorowan, Jogo do. Godo. Dolo on the mall. Yeah, you'll go. Kare see the Korean. Yeah, walk still. Oh, you'll go and see. The triangle is actually very important. The triangle itself is the core of the workshop. It's very simple, right? It has 3 vertices and connectivity. That's it.
Wow, just 3 points and how they connect? Seems almost too simple. So why the triangle? Why is it so fundamental in mesh design?
Well, triangles have some really useful properties for computers. First, they're always planar.
Meaning flat?
Exactly. 3 points, as long as they aren't in a perfectly straight line, will always define a flat plane. This makes calculations much simpler and more predictable for the software.
Okay, predictable is good for computers.
Definitely. And also, any other polygon-shaped squares, pentagons, anything more complex can always be broken down into a set of triangles.
Oh, right. You can slice them up.
Yeah, it's called triangulation. So using triangles ensures that the mesh is always made of these basic manageable units, no matter how complex the overall shape looks.
So when I'm looking at some incredibly detailed 3D model in a game or something, it's essentially just a massive collection of tiny triangles stitched together.
That's exactly it. Millions, sometimes billions of them. And the workshop material has a nice way to think about this hierarchy. It says, Obule.
Although they aga your roll yo moyo yo oh yo go yo goya, which means roughly. We have this big entity called a mesh. Explaining it hierarchically, right? So within a mesh, there would be countless vertices and countless faces.
So it's like a hierarchy. The mesh is the whole thing.
It's a big entity.
And inside that, you've got loads of faces.
Countless faces.
And each face is made of vertices.
Exactly. Think of it like a digital mosaic. Each little tile, the triangle, contributes to the whole picture, your 3D shape.
Okay, that makes sense. So we have these building blocks, vertices, faces, connectivity, often triangles. But how does the computer actually, store all this information? How does it keep track of potentially millions of points and connections? Good question. That brings us to beta structures. How do we organize all those vertices, those points in space? The workshop materials highlight two main ways.
Okay.
Using 2D arrays, or you could think of them as lists of lists. And the other way is using 1D arrays, just single flat lists.
2D arrays, lists of lists. That sounds kind of intuitive, like maybe a grid?
Precisely. Imagine laying out your points in a grid, rows and columns. A 2D array maps directly onto that idea. The workshop puts it like this.
Yo mito. Damujonyo. Yo jonyo. Axbayo. Axbayo. Aijo. Ayanyon tionyan.
Okay, let's break that down.
It translates to, there's a case where you put points in a list, and then there's a method where you put one row, then another row, and so on, entering them as X, Y, or IJ.
IJ, like row and column numbers?
Exactly. IJ, or sometimes UV coordinates. It refers to the indexing in that grid. So if you know the row number, say A, and the column number, say I, you can directly find that specific points data. Very easy to understand and access. Yeah, that makes perfect sense if your points naturally form a grid. But what about the other way, the 1D array? A single list. That sounds less straightforward.
It is in some ways. With a 1D array or a single list, you just store all the vertices one after the other in one long sequence.
Just one giant list of points.
Yep. The workshop explains, quoting again, Jenna, yeah. Jinda John you mean anyway. We put everything into one list, put it all in, right?
Yeah.
If I were to index this, I would have to use the number 12. But how do you calculate this? You can calculate it like this. 8 is calculated like this, I plus JU.
Okay, so K is the position in that single big list.
Right, the index.
And I and jar are like the imaginary row and column it came from.
Its conceptual position in the grid, yeah.
And U is?
U, or U dimension, would be the number of columns in that original grid. Essentially, how many points were in each row before you flattened it.
Right. So you take the grid, flatten it into one line, but then you need this formula just to figure out where a point was in the grid or which points are its neighbors. Why do it that way? Seems more complicated.
It can seem that way. Accessing a specific point requires that calculation. But storing data in one flat 1D array can sometimes be more memory efficient, particularly for really, really large meshes.
Memory efficiency. Okay.
But like the workshop implies, when you need to do things like find neighboring vertices to actually build the faces, you have to do those index calculations. It's less direct than just looking next door in a 2D grid.
So it's a trade-off then. Maybe save some memory, but some operations get a bit trickier.
Exactly. A classic computer science trade-off.
Okay, so we understand how the points and their connections might be stored. Now, how do tools like Rhino, like Grasshopper, actually take this data and poof, make a 3D mesh appear on screen?
Well, the workshop touches on the programmatic side of this, using something called Rhino Common. That's like the underlying toolkit for Rhino.
Okay.
The basic steps are, first, you create an empty container, basically a blank mesh object.
An empty box for the mess.
Pretty much. Then you start adding your vertices one by one, telling it the X, Y, and Z coordinates for each point, mesh, vertices.add, X, Y, Z, that kind of thing.
Okay, filling the box with points.
Exactly. And the final crucial step is defining the faces. You tell the mesh object which vertices to connect. For a triangle, you'd basically say, make a face using vertex number 5, vertex number 12, and vertex number 27 using their indices.
So you're literally giving the computer a shopping list.
Yeah.
Here are the points, and here's the recipe for connecting them into triangles.
That's a great way to put it. And the workshop notes that you can do this using different scripting methods within Rhino and Grasshopper, like RhinoScript or Python.
Automating the recipe.
Precisely. This programmatic approach is super powerful. It lets designers generate really complex shapes based on rules, data, algorithms, not just by hand.
Right. Once you have this digital mesh created, it's not just a static statue, is it? You can actually dig into its data, understand it, and even start messing with it.
Oh, absolutely. It's a living data structure. The workshop talks about how you can access and understand the information within the mesh.
Like what kind of information?
Well, a fundamental operation is iteration, looping through all the vertices, or all the faces. The material mentions shoja, yo-yo, meaning you loop through all the vertices.
So you can like visit every single point or every single triangle and do something.
Exactly. Apply the same operation or check some property for every element. Very common, very useful.
And the concept of normals comes up a lot in the notes. What exactly are normals and why are there different kinds like vertex and face normals?
Right. Normals. Think of them as little arrows pointing straight out perpendicularly from a surface. They're absolutely critical for how 3D objects look, especially with lighting and shading.
Okay, arrows pointing out.
Now, you have face normals, one for each triangle, pointing straight out for that flat triangle surface. If you only use face normals for shading, you get that faceted, sharp-edged look.
Like low poly models.
Kind of, yeah. Then you have vertex normals. There's one for each vertex, and it's usually calculated by averaging the normals of all the faces that meet at that vertex.
Averaging the face arrows around a point.
Exactly. And when you use vertex normals for shading, it tends to smooth out the appearance, making the object look more curved and rounded, even if it's made of flat triangles.
Ah, so that's how they get smooth-looking models from triangles.
That's a big part of it. And naturally, the number of vertex normals matches the number of vertices, and the number of face normals matches the number of faces. Understanding the difference helps you control the visual style.
Got it. The briefing doc also mentioned calculating face centroids. What's a centroid?
A centroid is just the geometric center of a shape. For a triangle, it's the average position of its 3 vertices.
The middle point.
Yep. The workshop explains how to find it. A XYZ jaw. XYZ jaw. Ejaha. Oh yay. Ejaha.
Translation.
If you add up the XYZ of A, B, C, the vertices, and divide by 3, you'll naturally get the centroid. We learned that in the vector class. So add the x's, divide by 3, add the y's, divide by 3, add the z's, divide by 3. Simple average.
Straightforward enough, and it sounds like you can also get the area of each face.
Yes, usually using the vector cross product between 2 edges of the triangle. The length of the resulting vector is related to the area.
Okay, vector math involved there.
A little bit. And related to that normal vector calculation, the workshop really emphasizes unitizing them.
Unitizing, making them unit length.
Exactly. Making their length equal to 1. The quote is,
Anagon.
Ching-yang!
Okay, Hoya Kim. Yeah. Yeah. And your J is John Yo Che.
Yungan John Johnyo, clucking on the green in the Saliying. In the 16th CTA ETH, Bergo Inchikand Ian Sanherladia, Kogemaning in Falose.
By Uring and Brune. Oyugan. A gamer. I'm gonna go. Let's unpack that one.
It says, since you did the cross product, if you unitize the resulting vector, it becomes the normal vector. Why do we unitize? What happens if we don't? Right. We don't know. The vector can get bigger or smaller. The vector length changes. But by creating a unit vector, we clearly get only the direction.
Ah, so the cross product gives you direction and magnitude related to area, but unitizing throws away the magnitude part, leaving just the pure direction.
Precisely. You get a clean, consistent direction vector, length 1, regardless of how big or small the face was. Very important for consistent lighting and other operations.
Okay, so once you have this mesh, and you can access its vertices, faces, normals, centroids, you can really start to play with the form itself, right? It's not just static.
Absolutely. That's where it gets really fun. The workshop covers different manipulation techniques. One key one is mesh offsetting.
Offsetting.
Yeah, basically moving every vertex outwards or inwards along its normal vector direction by a certain distance.
Pushing the surface out or pulling it in.
Exactly. The material describes it like this.
Which means you can just grab all the vertices, move them along the normal direction by the given amount, say 10 units, and the connectivity follows. The triangles stretch or shrink but they stay connected.
Neat, so you can make things thicker or inflate them.
Yeah, fundamental for creating shells or just changing the volume.
And I assume you can also do the standard things like move the whole mesh, rotate it, scale it up or down? Oh, for sure. Since the mesh is defined by its vertex positions, you just apply the transformation, math translation, rotation, scaling to all the vertices, and the whole shape moves or changes accordingly.
Makes sense.
But you can also get much more sophisticated. Procedural manipulation,
Procedural.
meaning the change isn't uniform. Maybe you move vertices based on some property, like move them further if they're closer to a certain point in space, or less if they're further away.
So the manipulation itself is driven by data or rules.
Exactly. That opens up a huge world of dynamic, responsive, complex forms that you couldn't easily model by hand.
It also sounds like you can get even more granular, like actually editing the mesh structure by removing parts, like faces.
Yes, definitely. The workshop mentions programmatically removing faces. You basically just tell the computer, ignore the connection between vertex A, B, and C.
You delete the triangle, but not necessarily the points.
Often, yes. The vertices might still exist in the list, but the instruction to form a face with them is gone. The material notes,
Oh, ooh, ooh, you, Owen.
meaning,
The vertices are probably the same. It's just that the data about the connectivity for that face is gone. It's like snipping the threads in that mosaic.
useful for making holes or openings, I guess?
Exactly. Or for more complex topological surgery on the mesh. And this leads to the idea of topology edges that are only connected to one face instead of the usual two.
Like the edge of a hole.
Precisely, the boundary lines, the open edges of your mesh. Identifying those is important for analysis and further operations.
Okay, so we've built it, we've analyzed it, we've manipulated it, maybe even cut holes in it. How do we then, save this masterpiece? Or share it with someone else? Or use it in a different program?
Right, you need to get it out of the computer's working memory and into a file. That's where serialization comes in.
Serialization sounds serious. It just means converting that complex mesh data structure in memory into a linear format, a stream of bytes that can be written to a file or sent over a network. The workshop puts it this way. Jim yohon jaliga, kayo barojim, kayo kimyon, yayogrim, retoyo goholeiton, te akayo grioyaga galeoakoyon, jogaya, jogoleogai, zao.
Gojo John.
Okay, which translates to?
Something like, there's a concept called serialization, as I mentioned before. It's the concept of how to pack data, transfer it, and put it back in. Packing it up for travel, essentially.
And there are different ways to pack it, different file formats.
Loads of them. The workshop mentions common ones like JSON, OBJ, SDL, FBX, GLTF. Each has its own rules for how it organizes the vertex data, the face data, normals, texture coordinates, maybe even animation data.
Why so many?
They're often optimized for different things. Like OBJ is relatively simple and text-based, often good for just transferring geometry between modeling apps.
Okay.
STL is very common for 3D printing. It basically just stores the triangles, making up the surface, nothing else usually. Right, just the shape.
Then you have things like FBX, which is common in game development and animation because it can hold lots of complex scene information. And GLTS is designed to be compact and fast to load, especially for web and real-time applications.
So the format you choose depends on what you want to do with the mesh next.
Exactly. Different suitcases for different kinds of trips.
This is all incredibly powerful for just, making and changing digital shapes. But how does understanding these mesh nuts and bolts really connect to the bigger picture of computational design?
Oh, it's absolutely fundamental. Understanding meshes is understanding the language of digital form in many ways. It lets designers go way beyond just using the tools and shapes provided. You can start creating your own forms based on data, rules, analysis.
Creating with code, essentially.
Yes, and the workshop introduces a really key idea here, using metrics to evaluate designs programmatically.
Metrics, like measurements.
Kind of. Quantifiable criteria for judging a design. The quote is,
Jan. Jan skada salga. Jono, Jonya, Jona. Dolo. Jona, Dolo. Kana no.
meaning,
You will create design metrics later. There is data, and you create a function that collects this data and can evaluate it.
so you define what makes a design good, maybe efficient or strong, or letting in the most light in a way the computer can measure.
Precisely. You turn your design goals into quantifiable values that can be calculated from the mesh data. Maybe it's minimizing surface area for material use, or maximizing volume, or analyzing curvature, or checking distances.
And then the computer can analyze different designs based on those metrics.
Exactly. You can write algorithms to automatically generate thousands of variations of a mesh, and then use your metrics to filter, sort, and find the ones that perform best according to your criteria. It allows for optimization, data-driven decisions, exploring possibilities you'd never find manually. So computational design isn't just about making cool shapes, it's about encoding design intent and performance into the process.
That's a huge part of it. Translating ideas into data and algorithms that operate on that data, often represented as meshes.
This is all incredibly insightful, it really is, but it also sounds like something, well, something you really have to do to understand, not just listen to us talk about.
Oh, 100%. Theory is one thing, practice is everything here. The workshop material hits this point hard.
Okay, what's that saying?
When you look at it, the code or the concept, you nod your head. But try coding it without looking. Is it possible? It's really important. You need to get to the point where your hands are used to the basics.
Yeah, the nod along but can't actually do it problem. I know that feeling.
We all do. It's like learning an instrument or a language. You can read the music theory, but you won't make music until you practice the scales, practice the songs.
Gotta get your hands dirty.
Exactly. And the instructor in the workshop used a nice analogy comparing it to climbing a mountain. They said,
여자수정. Oh, Jono, 사발래. 노이젠, 어디야 저전, 유전오전. 유전오전아. 우자den, spinozogen. 노이젠 유룩전.
let's hear the translation for that too.
Everything. The process is very important. So coding and things like that are actually language training, like practicing a language. It's not something where you get a sudden realization and it just clicks perfectly. You just have to do it consistently.
Consistent effort. Keep climbing the mountain step by step.
Way, really, building that skill and intuition over time.
Okay, so let's try to wrap this up. We've taken a deep dive into, well, the fundamental bits of digital meshes, the vertices, the faces, that all-important connectivity, often triangles, the building blocks.
We looked at how that data gets organized, 1D lists, 2D grids, and how tools like Rhino and Grasshopper actually build meshes using that info.
From data structures to visible form.
Then we explored accessing that data normals, centroids, and using it to manipulate the mesh, offsetting, transforming, even cutting pieces out.
Analyzing and modifying.
And finally, saving it all through serialization into different file formats and connecting it to the bigger idea of computational design using metrics.
Bringing it all together.
It really feels like understanding meshes is a critical first step into that whole computational world.
It absolutely is. And what's really powerful, I think, is how understanding these, seemingly abstract data structures really empowers you, the listener.
How so?
Well, you move beyond just being a user clicking buttons. You start to understand the underlying language of the digital forms you're working with. You see how the tool works, not just that it works. Gives you more control, more insight.
Definitely. You engage with the design process on a much deeper level. So here's a thought to leave you with. Now that you've had this glimpse into the world of meshes humming away beneath the surface, how might really understanding these digital building blocks change the way you approach your next design challenge?
Good question. What new possibilities open up?
Exactly. Something to chew on. We definitely encourage you to maybe revisit those workshop materials if you have them, or just look at 3D models with this new perspective, see what questions pop up.
Keep exploring, keep practicing.
Absolutely. Thanks for joining us for this deep dive.